Okay, good morning.
Yeah,
over to me. Okay, I'll start this. Good morning, everyone, and welcome to this seminar as we have named AI as a tool for change. And can we take the next picture? And today the people are talking. It's me, Jeanette Nilsson, working for RISE as an AI ecosystem driver, and my job is to try to connect the companies and public authorities and other organizations with researchers in RISE, and also working to see that we can use this tool much better. And Erik?
So thank you. Yes, I'm a researcher at RISE, a machine learning researcher working with applied machine learning. My main expertise is in deep learning, especially the kind of deep learning which uses complex data as inputs, such as sequences or text or graphs for that matter. I also do a lot of training, and this is one example of such a thing, about AI and about deep learning, both technical and non-technical.
Thank you, Erik. And RISE is the research institute in Sweden. It used to be a lot of different institutes, but then we just merged to one big. So we are one of the biggest in Europe, and we are spread all over the country, and we have all different kind of expertise areas, as you see on this slide. So we are a big research organization, but we work on computer science department. And then next one is this project that we are part of, because Europe wants to enable better competition and better possibilities for industry and research to use the large infrastructure on supercomputers, HPC, that are being built in Europe. And we are in a project with I think it's 31 countries, not just European Union member states, but countries that want to participate in building this network of enabling high-performance computing resources, both to companies, but also to research. And we are part of this group, and you can see more and go to this website, because it's a really easy to find, and you can find a lot of training that is free of charge to participate in, and a lot of other things that we do. So please subscribe to the newsletter if you don't, and find more information on this website. So the program today is about, firstly, as you heard, that Erik is an expert, and he is going to talk a lot about AI, data machine learning. And then we have a break and dialogue. And to the dialogue, you can send questions to me. So we will have a dialogue on other things that Erik has talked about, or other things you are interested in. And the last hour, we're going to focus more on AI as a tool for change. And as a starter, I can say, when I started working with this, I'm working and leading a work that calls AI Agenda for Sweden, from the ministry, that we are trying to have more people to use this and see the possibilities. I meet often these two kind of thinkings. The one is that AI is super intelligent. You can feed it with any kind of information on the internet, and it kind of like a detective thinks, this is what they want. And then they kind of like Terminator, but a good Terminator just make this happening. So I mean, a lot of people think that it's kind of like both in a good or bad way, like some kind of some magic things happens. And also that people talk about, they don't really know what data is. It's like they say, data is gold, and they think that data, now they have a lot of kind of money, or that is a new oil. And if you think so, then it's so hard to talk to people. So that's what I meet. And today we are going to also to diffuse these two. And so I give the word back to Erik, and to make the first presentation.
Thank you very much, Jeanette. And I would kind of even though I started from the computer science background when I met AI first, I also was in awe. And I think this picture which we showed, this idea of this very intelligent thing being able to learn from a lot of different sources to get this really exhaustive understanding of a problem. And also this idea of something which is able to adapt, to learn, to dynamically address new situations and new problems. This was really also my first impression of AI, and also how it's often communicated. But then when working with AI, you soon realize that a lot of AI, at least a lot of AI in practice, is actually more akin to statistics. So what we did in statistics, if you've done that. So we have, a few, ideally, variables which we would like to understand the relationships between. And we would like to then be able to understand what would happen if we change variables, for example, or when we see a change in these variables, we can kind of follow what would be the change later on, for example. And then that these systems are often, they're implemented in software, and like any system in software, they will have bugs and they will be brittle, perhaps even more so than general systems. And this idea of, this, we represented it by the Terminator, but this agent which can adapt, can understand, can kind of be better than a human in a lot of senses. That turns out to mostly be a fantasy. So these kind of pictures of a robot kind of interacting with some kind of circuit, sometimes a brain circuit or something like that, that kind of gives the wrong impression about AI. And when meeting with people, and actually like me, I want to do AI. With AI, we can do fantastic things, but this perception, this miscomprehension of what AI is in the way. In particular, it leads to inflated expectations, which is often not a good thing when you want to do things in the real world. Then when I started working with this field of AI, I really realized that data is super important. And these liking data to oil or to gold or to rocket fuel and so on is, there is reason for using that metaphor to try to highlight how important data is. But I think this metaphor is in a lot of ways flawed, because gold and oil are kind of these things which have some inherent value, and it's more about finding where it is. But once you find it, it will be great. And it's also just there. New gold isn't produced, well, at least not on Earth, and new oil isn't really being produced. So I think a better analogy, which I'm going to use a couple of times in this talk, is that of waste, and perhaps in particular of electronic waste, e-waste. So data is the new e-waste. There's a lot of similarities with e-waste in the sense that data is a byproduct from some other source. It's not just there, typically. It's created by some kind of process. And if we are an organization, it's usually created by some of our business processes as a byproduct. Now we can, if we're scientists, for example, and doing research, sure, then we try to gather data to understand a phenomena. But in practice, if we want to develop a new AI system, for example, in an organization, we often want to do that for existing processes. And then the data generated will kind of be data from a process. But then also that it's hard to understand. It's kind of this pile, depending on how well we have managed our production of this data or of this waste, so to say. And also that it changes over time. There are differences based on where the origin of the data, so sorry, you can see my screen, right? Thank you. And I think an important point to highlight here is that we can actually change what kind of data is being produced. So just like with waste, we can manage the waste and how we produce the waste. So in difference from oil or gold, for example, where that's kind of just out there and valuable in and of itself. And finally, often we don't actually know whether what we have has any value at all. But if we believe that it has, another thing which I like with this analogy is that it requires quite a lot of effort to go from what we have. Perhaps it's data in our, we might have a database which is structured, but it's not structured according to what we would like to do with AI, for example. It might be structured for some other reason. It could also be quite unstructured. It's more just a big lake where people have dumped things, kind of like a rubbish heap. And then trying to go from what we have in terms of data to what can be used for AI requires this process of actually, going through the data, sorting, kind of like how we do recycling, and then eventually finding the relevant parts of data where much effort to process that will be we will need to use a lot of effort to actually get to what's actually the valuable part of the data. So that's kind of the data, and I start with that because often this is one of the most important things when it comes to what can we do with AI. But then the question is, what is AI, and also what is machine learning? So this representation, or this kind of depiction of what AI is and its relationship to machine learning, is one I like to use. So you can see on the right hand side here we have this kind of onion where we have AI as this big, the largest area of this, and then there are subfields within this field of AI. So I typically define AI. There are no kind of consensus on the definition of AI, but a common one is that it is the study of machines which can solve problems which humans solve by using intelligence. Not that they have to mimic the human intelligence to solve those problems. This has often been, throughout the history of AI, kind of a disappointment. So for example, when Deep Blue beat the then world time champion Garry Kasparov in chess, people were disappointed because the actual AI used was not something like human intelligence and human learning and how a human plays chess. We've seen this again and again. But this is still being done in the field of AI. I mean, it's unquestionable that Deep Blue was actually an AI system, but it was not a system which learn and think like humans. And this is actually quite a small field within AI, the study of machines that do think and learn like humans. Even though a lot of AI researchers might find that inspirational, most of the actual work being done is more akin to the first point there. Today, the term AI has kind of become, in a way, conflated with the term machine learning. So a lot of times when you see in the news, an AI did this, an AI beat a human in Go, an AI beat a human in chess or StarCraft or some game like that, or an AI can now do some kind of medical diagnosis, it's often actually some variation of machine learning being used. So machine learning is a subfield of AI, which is about machines learning to solve problems. And this is what we'll focus on today. So this conflation with AI and machine learning, it is wrong, but it is often what people mean today when they talk about AI. This can change. So to understand AI, I will talk a bit about algorithms, because essentially AI is some form of algorithm. It is implemented in software. It is something which follows a sequence of steps to solve some problem. And we often, an algorithm kind of attacks a problem by looking at some input or a state of the world before the algorithm starts. Then it follows a sequence of well-defined steps and ends up with the state after the algorithm, or an output. And these algorithm then decides, what is the relationship between input and output. And often we want to do something useful with this algorithm. So for example, we might want to do division. And long division is an algorithm which a lot of people have learned during school, where we get this simple series of procedures we can follow to actually solve a problem which we could not solve just intuitively and directly in our head. And it's also a good illustration that an algorithm isn't necessarily something which runs on a computer, though it's often very useful to run them on computers. And computers are actually, they need algorithms to do something useful at all. Another analogy which I like to use is that of a recipe. So this is kind of an intuitive way of understanding what an algorithm is. So we have a recipe to cook something. We start with some ingredients, and then there's steps of procedures. So the ingredients would be the input, the procedures, which we should follow the recipe, that is the algorithm. And we are kind of the thing executing the algorithm. And then we end up with a cooked dish, which is the output. And a computer is kind of a thing, kind of a very stupid, very narrowly minded chef, which follow things exactly as you described them. That is one of the challenges with writing algorithms, is that some problems are very hard to define in instructions, which humans can easily write, which humans can express. So this is an example. This is from XKCD, one of the popular nerdy comics on the internet. But it can be very hard to understand the difference between two problems. So in this case, it's about tagging photos. So looking up where the photo is taken can be quite easy if we have access to the positional information within the metadata of that photo. But actually saying what's in the photo is very, very hard to write a program to do. And this is kind of where we then go to what we call learning algorithms. So imagine we have this algorithm which takes an input and an output. A traditional program, a rule-based algorithm, it's a computer program. It is written by humans, often, but mainly by humans, with clear instructions which describes how the problem should be solved in a programming language, typically, but there are different ways. But some kind of sequence of rules the computer can execute to go from input to output. So learning algorithm is kind of the same idea, but it's not these instructions written by humans. It's more kind of like a mixer board or an analog filter. So we still have this input, and if you think of a mixer board, the inputs would be signals, sound signals, audio signals. And we have all of these knobs we can turn to actually change how these signals are filtered or mixed together to get an output. So think of the input here as being audio signals, output is also an audio signal. And with learning algorithms, we can by optimization try to find good settings of these knobs so that they actually do the algorithm we like, without knowing ourselves how we'd write that algorithm. So the hope then is that by doing this, and I should also mention that the way we understand how to turn those dials is by looking at data. So we have data which guides how we should turn these dials to get a good setting. And then by doing this, then perhaps we can actually still have an algorithm, but it's not defined by human using rules. It's defined by this optimization procedure using data. And the hope is that this algorithm will actually outperform what we could actually write down in terms of rules. And this is something we have seen for a lot of different problems where it was previously very hard to do things with rule-based algorithms, which we'll come back to in the last act of this seminar. So this is kind of the introduction. We will not go a bit more into depth about machine learning than this, but we'll do that in the context of what we'd call a machine learning checklist. So often you might wonder, is machine learning suitable for what I want to do? I have some task I would like to solve more efficiently, or a task which we can't currently solve automatically at all. Could I use machine learning to do this? So in an article by Erik Brynjolfsson and Tom Mitchell. So Erik Brynjolfsson, you might know from he's a co-author of a book called The Second Machine Age, which is about kind of the digital transformation of society. But he's written this article, which is about kind of the future workforce implications because of AI. It's a couple of years old, but it contains an interesting kind of checklist of where machine learning is suitable. So we've adapted this checklist a bit into 6 points. So these are the 6 points where to determine whether the thing you have in mind is suitable for AI, you need to go through all of these 6 points and tick them off and say, yes, this holds for my problem. So the first one is that it can be described as a function from well-formed defined inputs to well-defined outputs. There should be large quantities of digital data in input-output pairs, no long chains of logical reasoning, and no common sense or world knowledge is needed. There should be no need of an in-depth explanation of why a decision was made. Errors can be tolerated. There is no need to have a provably correct solution. And finally, that no dexterity or physical skills or mobility is involved. So we'll go through this one at a time, and I'll go more into depth about what we mean by them. So first of all, this can be described as a function from well-defined inputs to well-defined outputs. This is kind of, I already talked about an algorithm, and this is kind of just making that a bit more clear what we mean with what kind of algorithms we're talking about. So one example a lot of people might be familiar with is that of a spam filter. So imagine you have a lot of emails, and some of them contain, well, just spam. Unsolicited emails to kind of fool you to buy something, or pure scams, for example. So you would like to automatically sort those out because you get far too many of those kind of mails in relationship to the mails you would actually need. So here we can think of the inputs here. Those are messages, text messages, emails, and then the algorithm is something which can classify these two messages. And the output is a classification. So it's assigning the message the class spam or not spam. So this is a commonly used example. Most of us, or all of us who use email, use a spam filter, even though we might not ourselves have implemented it, likely haven't. Other examples, so one from speech recognition. The input might be an audio signal. Here the mixer board is the learning algorithm, and the output in this case is text, so the transcribed text. Or a common example we've seen being publicized a lot is that of computer vision and image recognition. So the input is an image, the output is some kind of decision based on that image. So for medical diagnosis, it might be a heat map on the image indicating some kind of diagnosis. It could also be a classification of images, for example, saying, well, this is an image containing a cat or a dog, or it could be facial recognition saying, this image is very close to this other image I have in my database. And then a question of what is, when don't we have well-defined inputs and outputs? And often this is a case where we don't really know what kind of information would be necessary to answer some question, make some prediction. So if I just would like a system to learn, what I have done, just asking a question, for example, isn't enough information. But a lot of problems can actually be modeled as this function from inputs to outputs. Often if we add perhaps more inputs, so this would add context which the learning algorithm can actually use to be able to answer this question. So this first point is actually often with creativity, we can come up with a way to model our problem like this. But it might make it infeasible to do it because these things we need, so for example, our movement history or our chat history and so on, might be something we cannot get access to or are not allowed to get access to. So then number two, and this is one of the really important ones, there should be a large amounts of data in the form of input and output pairs. So we've already seen the inputs and the outputs. Let's go back to this example of this spam filter. And here I'll explain a bit more about how these methods are how they're built. To start with some kind of problem, in this case, the problem is that we would like to go from documents, emails as inputs and classify them as spam or not spam. So the inputs are emails, the output is a classification. It's a binary variable essentially. The machine spits out a 1 if it's a spam or a 0 if it's not a spam. But to be able to build this text classifier, to turn these dials on this mixer board, we use data. And the way we do it is that we have something we call training data. This is kind of reference data, which we use to find the settings on the mixer board. So this training data, we take that. Here you can see that we have annotated the data, and we would like this text classifier to be able to find that annotation, to split the yellow from the blue documents. But it's still the same problems. This is just more general formulation of it. It's document classification, but spam filtering is an example of that. And then we use this by trying to make this classifier actually put the documents in the right place. We train the system, and we do this by turning these dials in the mixer board I showed you previously. And we have a procedure which automatically does this. So the training procedure knows how to turn the dials. That is not something a human has to be involved in. But it will typically be able to do this perfectly on the training data, because there will be enough patterns in the training data, or it could find any patterns in the training data until it finds patterns which it separates the data, but is not actually solving the general problem. So this general problem, or the problem of actually for a new document or a new mail, I would like my method to do the right thing. This is what we call generalization. Perform good on new data you haven't seen before. And we evaluate our systems during training by putting away some data before training and using that to actually try to gauge what is the real performance of the system on new data. And this is what we call the test data. And these procedures are hungry, so we often need a lot of this kind of data. To be able to say anything about the reliability or the utility of a system, we at least need test data. So we need something to evaluate our models. And this data needs to be large enough that we can say something, that we can try to quantify how good our system is. So often this will need to be, best case, 100 data points. Then we can say a bit more about how reliable our system is. If it's only 10 data points in the test data set, that is not enough to actually say something sharp about our system. We can use statistical tricks to try to get more out of our data, but with 10 data points, we can do anything with these methods. With hundreds, perhaps, and with 1,000, then we can at least do a reasonable experiment, even though our system might not perform well at all. So one of the, as I said, we need large amounts of data, but we also need this data to actually be labeled or annotated. So you can see this picture shows us we have this large data set of documents. And then to build our training data, we select some of them and we try to assign a class to them. Now this assignment process or labeling is often done manually by humans if it's complex data. And that labeling might actually contain errors. So by human error, perhaps you misclicked something in the tool you use to annotate the data. Perhaps you just misunderstood something, and so on. So then this annotation is really perfect, and it's time consuming and costly. But it's still, this is kind of it is in this part of the project where we actually define our problems. So by deciding, which data should have which label, we decide what the desired output should be for each input. So in this case, the inputs are documents, and the output is the color of the document in this case. And this annotating of data, that is often very, very critical, but also very time consuming. So for your problem to be suitable for solving with machine learning, this is essential. And being able to put effort into doing this annotation, that is also really important. So enough of that, and move on to interesting question where people, me included, in the beginning, Jeanette told about this, this Terminator or this Sherlock Holmes kind of idea of AI, this really powerful reasoning agent. But for machine learning to work, we can't have long chains of reasoning. So to think about kind of what are actually the capabilities of machine learning today, I should say, it is good at doing things like recognizing faces, but it's bad at doing things like answering a question, what are the macroeconomic effects of falling oil prices, and then following a chain of reasoning to reach a conclusion based on facts about the world. This is something we cannot do with machine learning. We can do this with AI. So what's called good old-fashioned AI, or AI which was about kind of reasoning and logic, have very powerful algorithms for doing this. But one of the main problems there is actually writing down the supporting facts for this algorithm is a major challenge. So those systems typically don't have any learning in them. The human has to supply all of the knowledge to the agent, which then becomes a prohibitive task. And kind of following on this is this unfortunate thing that we cannot, even though we might have very clear instructions of how problems should be solved, clear for a human, for example, we cannot use those instructions for a machine learning agent. So for example, we had a project where our partner had a lot of documents. So they have a lot of documents which should support some decision, but they also have very clearly defined policies of how to make a decision based on these documents. So they hope that we have a lot of this data on how to support the decisions, but unfortunately, machine learning cannot really read those instructions and execute them. Instead, machine learning has to more learn how to do things kind of like how we learn to ride a bike, or how we perhaps learn to I don't know, juggle or something. It's not a perfect analogy, but it's more like machine intuition rather than machine reasoning. Then no need of an in-depth explanation. And this is something which has already been highlighted kind of in media, that our models tend to be kind of like black boxes, that we don't really need, we don't understand how the function looks, which goes from a spam message in this case to the prediction of spam filter. Some models we can inspect and say, oh, it seems to highlight this word a lot, Bitcoin, okay, it's probably spam. But often, especially the complex machine learning systems like deep neural networks, which we use for image or computer vision, or which we use for more complex analysis of natural language, these we cannot understand how they reach a decision. And this is, of course, can be a major hurdle if this system should be used to make decisions which affect human. We'll talk more about that in a couple of slides. So this is a really active area of research, but it has been proven to be very hard to actually make what's called explainable AI, in that we have this computer vision system which can say what species of bird this is, and it seems to have high accuracy, but we would like to understand why does it say that this is a certain kind of bird. Then a lot of methods have been developed which essentially creates a heat map on the image which say, oh, the model is looking here. But it turns out that heat map might not really tell us what we think it tells us. So kind of like we don't really trust this black box, this heat map generation is also kind of a black box which we don't understand, even though we think we might. Here's a reference to an article where they talk about, they show how unreliable these explainability methods are. But there's a lot of research here, and especially what's called interpretable AI shows promise. So then the next point, and this is really a very important one, no errors can be tolerated. No need for provably correct or optimal solutions. And this has to do with that these methods are essentially, they are advanced statistics. They use statistics to reach their, understand how to make a decision. And these decisions will never be 100% correct. and will never be provably 100% correct. So I talked a bit about this test data earlier. That test data will just be a sample of any new data you could come across. So while you might get perfect accuracy on the test data, it doesn't mean that some new data point you have never seen before will also be correctly predicted. You can see this matrix I see here tries to illustrate this. So this is a binary decision prediction problem, where based on X-ray images, a computer vision model tries to say whether this is a X-ray of a chest from a person with COVID-19 or not. You can see that on the diagonal, those are actually the correct predictions. So it's pretty good at guessing it's pretty good at correctly assigning the COVID diagnosis. So it only misdiagnoses 2 people who actually had COVID. So you can see on the rows, you have the actual targets, and then on the columns, you have what the model predicts. But when it does that, it actually also produces a lot of false positives. And this will always be the case with machine learning, that you will have some kind of error, and that error you have to be able to accept that error. And we've seen a lot of examples where probably this is not acceptable. So I'll talk a little bit about this algorithmic bias, which is something which it has gathered attention, rightly so, because it is one of the dangers of automated decision making with these methods. So I could start from the left here. So early during the pandemic, a researcher wanted to automatically survey how many people in her city were actually wearing masks. So the city had public access webcams of populated streets in the city. So she thought, well, let's just first find the faces, and then I run them through one of the many computer vision APIs or services out there, which does the classification for me. So she did this, and what she saw quickly was that there was a very high skew on prediction based on the gender of the person being run through the algorithm, where a woman was much more likely to be the thing she had in her face was much more likely to be predicted as a facial accessory, for example, or worse, in the case of the Google system at that time, the top prediction for a woman and something covering the mouth was a duct tape. So this kind of shows that these systems, if there is some kind of bias in the data, and in this case, if you take fashion accessory, the reason for why the prediction of fashion accessory is so high here is likely because the data the model has been trained on, when it comes to fashion accessories, have been skewed towards women. So if it's something in the face for a woman, it's likely to be a fashion accessory. The model doesn't know much about the real world, so it kind of follows the statistics it has seen. It tries to condition this on what it can kind of actually see in the image, but these systems are not. They do not perceive an image like humans do. Another example, which got a lot of attention, is where another group of researchers, which tries to guard against these things, they took a image of a black man holding this is a what do you call it, laser distance measure tool to measure the distance to things with a laser, essentially, where hand is one of the top predictions, but gun is also one of the top predictions. And then by just with a really ugly kind of paint trick, changing the color of the skin, they change this prediction so that gun drops a lot in the ranking, which also kind of shows the dangers of if you were to use this for automating like policing, you can see that this would have a definite negative impact on society. Or another example, this is a group of Chinese researchers where they try to, from just mugshots essentially, predict whether a person is criminal or not. And what they show was that they had pretty good accuracy when it came to this. But the sources of these images was, well, one was true mugshots from the police, and the other was from applications to CVs essentially. And while it might be hard to see, is that, well, the people who are not criminals are all wearing a white collar shirt and a suit essentially, and are slightly smiling, while none of the others do. So there is kind of an inherent bias in the data, which, if people were to actually use this in real life, it might flag people who are not wearing a suit as likely to be criminals. And then an example from some of my former colleagues, so Magnus Sahlgren and Fredrik Olsson, together with the Swedish Bolagsverket, so that's the office for registrations office for companies. They looked at trying to automatically determine whether a name of a business is suited to the description of the business. So in Sweden, you can't have any name for your business. It has to actually be suitable for the business. You can call it Eriks Bilar if what you do is actually sell AI services, for example. So they looked at this, and then they looked at how they could actually, so bilar, for those who don't speak Swedish, that's cars. So this would be Magnus cars, Fredrik's cars, Maria's cars, Anna's cars. And then it's the exact same description for all of them. This company will work with cars, essentially. And they could see that if they changed the kind of the gender of the name, they actually changed how far away the model thought that the description of the business and the name of the business or the name of the company were from each other. So here, it also picks up on underlying biases in the data which has been trained to generate these measurements. So distance, essentially, the closer it is, the more suitable the model thinks that the name is. And the further apart, the less suitable. And then there are other issues like translation, where you might have a language which doesn't really have gender pronouns, and when you translate it to a language which does, this will tend to follow the kind of underlying biases of that language. Now this is a hard problem. So as you can see in the last example here, what should a model do here? What would be the best translation here? So we humans, we are often more aware of contexts. So it might be reasonable from the context to assume one pronoun or the other. But this model knows nothing about context. So the only reasonable thing it can do is go by the statistics of the data. And this is really I would say the danger of using these methods for automated decision making. So what we said here is that you must be able to tolerate errors. And then finally, no specialized dexterity, physical skills, or mobility is required. So there was a lot of attention given to self-driving cars, I would say, in 2014. So me included, I thought that this problem will likely be solved in 10 years. That we can already do really good computer vision was my thinking. We've already seen computers being able to play video games at that time. So Atari, for example, was being played at superhuman skill for some of the games, and the method for learning how to do that was very general. I mean, why couldn't it be used to learn anything, basically? So there about 2014, this idea of self-driving cars and completely self-driving cars, so robotaxis, became part of the general consciousness in a sense, and that in a couple of years this will be reality. And then as the years went on, we probably realized that this was very hard. And so first, before I talk a bit more of why it's very hard, just highlight what this kind of AI is. So it's still a form of machine learning, but it is a form of machine learning where we would like an agent to be able to learn through interaction how to act in a dynamic environment. So we have some kind of environment. It has some state. The agent moves around and should be able to learn while it kind of lives, in a sense. So we often think of simple learning like Pavlovian learning or Pavlovian conditioning in the same sense. That we might have this animal which we can teach to do something by giving it reward when it does the correct thing. And this branch of machine learning called reinforcement learning formalizes this and makes it into a very powerful framework. So the agent makes some action, the world changes based on that action, and depending on how the world changes, we reward the agent. The problem with doing this in machine learning is that these agents need a lot of trials. So we would like this environment to actually not be in the real world because that's too slow. We'd like it to be in a simulator. And this is where the challenge with self-driving cars comes from, I think. There is no chance of allowing a self-driving car to try to learn in the real world by trial and error, crashing 100 or 1,000,000 times before learning how to actually navigate traffic. That's not feasible. So we like to build a simulator. But building simulators where fidelity, being as close to realities as possible, that is very hard. So things like hydroplaning, for example, accurately capturing that in this kind of simulator where you take into account the tires, the road, how good the road is and so on, is very hard. Now that can probably be solved, and a lot of people, of course, model that. But that is just one example of all the things you would have to model. Another is kind of weather condition, mist, snow, what happens then with vision. And can you model that so that the thing in the simulator is close enough to reality that this agent doesn't learn, to misbehave, so to say. It learns a loophole when it comes to snow because the snow in the simulator follows a certain pattern, which the snow in real life doesn't. So it's a really hard problem. And that's one of the reasons for why the successes we've seen here is in computer games. So in a computer game, the two of the really important ones I should mention is AlphaGo and AlphaGo Zero. And then there's also AlphaZero, all from DeepMind, and then AlphaStar, which is also from DeepMind. So DeepMind is a research company owned by Google's parent company. They do a lot of really high-level research. It's one of the top research institutions in the world. But two of their very public achievements was first beating the then world, one of the top ranking players in Go, one of the most complex games for AI previously. It long was one of those holy grails of games playing AI. And then also beating another goal, a much harder problem, of actually a problem where you don't know everything that's going on in the game. But to be able to solve these problems, they need to use huge amounts of data. So AlphaGo Zero, while being much faster than its predecessor, still needed millions of games before it reached the same competence as its predecessor. And then AlphaStar was first trained to mimic humans on a large database of human play, and then played a huge amount of StarCraft against, copies of itself, essentially. And this works because we have the perfect simulator for computer games or for games like Go, that all of the dynamics of the environment are perfectly simulated in this simulator. So we can just use the game to train this agent. And also that if it makes a mistake, the only cost is kind of the waste of time, or it's not really a waste of time because that mistake is learning. It learns through that mistake. But we couldn't do this in the real world. So, and we couldn't do this for things where making a mistake might actually have external costs and perhaps even disastrous costs. So finally then, this checklist again. So we have these 6 points, which I hope by now they are quite clear. But I should also mention that a lot of what I've said here is under change. So this is a field where research is happening very, very fast. And I should also point out that most of what I say here is really about, practical AI. If instead you're interested in using AI as a part of, some kind of fundamental research, there might be, perhaps this simulator might not be a problem. You might actually have access to a really good simulator. or you might be able to actually produce lots of data through through some kind of other experimentation you're doing. But still, these 4 points, I kind of mentioned how this chains of logical reasoning is something which is very hard. But there is a lot of effort being put in to try to make these machine learning methods be better at doing those kind of things. And also to actually support them by this kind of fact databases or knowledge databases which have been curated by humans, so that they can actually use this as supporting evidence for something, which brings us closer to this being able to read a instruction or being able to use common sense or world knowledge to make a decision. And this really important point of interpretability, which I also think it's important to mention in terms of this algorithmic bias and trust of the methods. A lot of research is being done here, and smart ways of actually combining these complex models but still being able to make them interpretable are being done. And finally, this context-aware AI, more of a broadly that we can train the AI with complicated supporting contexts to the decision that's being made. But these are still really the research phase. This is not something you would try to implement in when you want to develop something for production. So in summary, this is a very vast field. So AI is much more than machine learning, but currently machine learning is what's dominate what we think about when we think about AI. And then it's mainly about solving narrowly very well-defined tasks, which we can kind of describe as inputs and outputs. A lot of tasks can be described as that, but it's more general. So imagine we would like to replace some human in a workplace. That is probably, that's not going to happen. We might be able to replace one very narrowly defined work task, but not a slew of tasks. And then we can use this checklist as a good first kind of filter on our IDs. And then finally, this point on artificial agents and agents which learn by interacting with the world. So imagine robots being out there and doing things in the world. This is a really hard problem. So we might have robot vacuum cleaners or robot mowers. But as most of you who have interacted with them know, that they are very, very simple. If they get stuck, they can do nothing about it. And we are far away from kind of this, the autonomy of a simple animal when it comes to robots. That has partly to do with the AI and learning part, but also to do with that robots is really hard, or making engineering bodies which are as robust as biological bodies. That's a real challenge, especially when it comes to the energy. Unless you can, sure, depending on context, you can use solar power. That's great for robots on Mars. We'll get back to that later. So that wraps up this first session. But before I end, I would like to point you to 2 resources if you would like to dig deeper. So the University of Helsinki have been developing, funded by the Finnish government, these massive online courses for AI. So they have one which I think was started in 2018, called the Elements of AI, which has now, through the help of the EU, been translated to a lot of different languages, including Swedish. So that's called Elements of AI. It has a kind of different perspective on AI and quickly becomes a bit more technical. So I would recommend that if you are a bit more technical. And then they have a new initiative they call Ethics of AI, which is more about this, what I talked about, the issues with automatic decision making in light of these algorithmic biases. So if you want to learn more, I would recommend you start here. There are so many resources out there, but this is a good start. So let's now wrap this up with kind of looking at what would we want to do with AI, and especially AI in an organization. That is the kind of context we would like to talk about. And we choose to say AI as a tool for change, to kind of highlight that AI is not in itself it doesn't do anything in and of itself. It is something we use to affect the change. And in particular, we will kind of focus on the idea that we have some kind of processes. This might be processes in some production. It might be processes in tasks we need to do. But there is something where we hope that by using software, we could make these processes more efficient. So I have an example here of doing retrosynthetic analysis in chemistry, but the main idea is just to say that we might have something which is complex. By introducing some piece of software, we might make it a bit more efficient. We probably can't replace this whole process by software. That should probably not be the goal, but rather to try to find where is the issues. And one thing, way of thinking about what AI gives to software is to take an analogy to 3D printing or additive manufacturing. So probably a lot of you know what that is, but essentially by building things in additive manners, we're able to manufacture things which would be very hard to manufacture with other, like subtractive manufacturing, essentially drilling bits away from a piece of steel. There are things you will not be able to get access to. But by additive manufacturing, you can build very complex geometries, for example. There might be lattices, it might be a lot of cavities and so on in the thing you're building. You might have differentiated in behavior and so on in the material. So essentially, additive manufacturing allows us to produce new things. So for some things we would like to manufacture, some parts, it will actually be only additive manufacturing can do that. We cannot do it with the conventional methods. But there will still be a lot of things we want to manufacture where conventional manufacturing makes a lot more sense. And the analogy then is that, well, think of AI as giving software new capabilities. And for some problems, or in some cases, it allows us to automate things with software which we could not automate before. But for a lot of things, using the conventional methods, so I'm calling those the rule-based methods, regular software programs, that will make most sense. And then also that there might actually be processes which doesn't make sense to try to automate. The cost of automation would be much higher than actually the cost we're currently paying for it being slightly inefficient, perhaps. So, and the way to think of AI then is kind of a toolbox or a general thing, like a programming language, or like programming perhaps in general. So the tool of programming, what can we do with that? And in some areas, in some applications, AI is more mature than others. So there are some kind of problems where we can get pretty far with current AI, where we might even be able to buy a product which does this and easily adapt it to our own needs. And then other applications where we probably need a lot more work. So we actually need to develop software. So just briefly going over kind of the capabilities of AI, this is just a small sample and to give you an idea of what is there. So images and what we call computer vision is one of the examples of recent AI success, that we can automate kind of analysis of images to a much larger degree than we could before, with much larger targets, so to say. So processing images or doing computer vision has been around for a long time, but has often relied on, for example, signal processing, where we can think of that as humans being able to find good ways to represent the images and then try to define rules based on those ways. But those are limited. So now with recent developments these techniques are actually from the late 80s, but with recent large databases, large high quality databases, we can now train machine learning systems to be able to do a lot of things with images which was hard to do before. So for example, actually classifying images or doing image search, recommend the things based on images, or do more more accurate fault detection or a quality assessment of images, for example, is a very common use case. We also see applications like image processing and so on, where we can do more efficient, for example, blending or cut and paste of images. Another example is video, which is kind of an extension of images. We have a sequence of image frames, and here we see a lot of applications when it comes to monitoring. So a lot of this is used in monitoring, well, perhaps crops, but also monitoring humans, which is kind of also in the area of ethics of AI. We see that we can monitor humans to a much better degree than we could before, or more accurately. And this, we're seeing a scare example of this around the world. Then autonomous vehicles are here because they typically use some kind of machine learning for the basis vision parts of the system, not for any of the decision making, but to essentially have a sensor of what's around the car. And there it's actually useful. So machine learning is used in autonomous driving, definitely. But I think the progress we saw with computer vision, and that we have this rapid progress in how fast our performance in this case is improved, that led us to believe that we could likely do self-driving cars well, because by looking around us as we drive a car, we're able to drive it. Was kind of perhaps a naive idea. I think a lot of people were less naive than that. I was that naive. But then another mature application is that of analyzing text. So we often call this natural language processing. So we have a lot of organizations have documents, lots of documents. These could be natural text. They could also be, as we talked about before, for example, they could be text generated in some system meant for a human to read. So perhaps incidents reports or installation logs or some kind of logs, but which are hard to automatically or to classify, for example, using rules. So this is where these methods from natural language processing come in, where one of the really important one is document classification, which we've already talked about. Another one which is often used is this named entity recognition, especially when it comes to internal documents as companies. You might have documents which describe, what you have done with other companies and so on, and you would like to automatically get that out. Or more question answering, for example, has been one of these hyped application, but it is important because essentially you would like to more efficiently search in perhaps large documents by queries and do this without having to have exact keyword matches and keyword queries, where you might to get good find good documents, you might have to chain together a lot of complex expressions, but you still miss a lot of the documents. So instead, using these methods which try to get at the semantics of the text instead of just the surface, keywords of text, we can actually do a lot more today than we could just 5 years ago, or 10 years ago, perhaps I should say. So this is one area where I do a lot of work. Then there's, I said those were kind of the mature areas. What I meant there is mostly that here is, so for computer vision, for text analysis, there are tools which you can purchase and which you can adapt to your process. But then when it comes to other kind of problems and other kind of data, this is typically where you will need to build your own models and do more, lay more effort into that. So structured data is what we typically call data which is in the form of tables, or in databases where there might be tables with relationship to each other. So this kind of data is really I would say, has been the majority of the kind of machine learning we have done up until perhaps 2010. A lot of machine learning was done on these kind of tables and was very successful. Unfortunately, people often didn't hear about them, but at our previous institute, the Swedish Institute of Computer Science, we did this kind of machine learning for a long time before 2010. I think starting early 2000, and perhaps even before. I wasn't there at the time, but we did a lot of machine learning but no one was really interested because it hadn't become this idea that you could do things with this. And this kind of this goes from regular statistical regression analysis that is kind of in the scope here, but then doing more and more complex models in these frameworks and regular kind of prediction. One important field here, which we often we have done a lot of work is anomaly detection. So essentially trying to understand a new observation, is it common or not? And if it is uncommon, try to do make some user aware of that. So going forward, so kind of related to structured data, sensor data, and IoT data. Most of them look kind of like structured data or can, but they are typically time series. So they are measurement over time, and they might be at different rates. So essentially, they are hard to put in a table because you get a lot of missing values in the table. But here we also see machine learning starting to be used to do more complex control. Still, here is kind of an intersection of traditional control theory and machine learning. There is a large overlap there. A lot of people who work with traditional control theory also do master machine learning, but there are reasons, or it can be complicated or it can be risky to use machine learning systems instead of the regular controls you would use in control theory. So at RISE, and especially here in Luleå, we do research on data centers. And one of the things we're looking at is autonomous data centers. So being able to control them autonomously, in particular looking at heating, for example, and cooling, but also when it comes to like how to schedule resources and so on. And then finally, another area where, or not finally, this is the penultimate example. Geometric data is one of my research areas. So by geometric data, we mean some kind of data which lives in some space. And often a property of this data is that it is not regular. It does not follow some fixed structure, so it can be arbitrarily sized. So for example, a molecule, where it's a field where I've done some work, where we look at using machine learning to take molecules as input directly. The molecule can vary in size, but we can still, with recent advances in machine learning, and in particular deep learning, we can take the molecule, the structure as is, as input to our methods. A closely related application is that of point clouds, where we might have an arbitrary number of points in a 3D space, for example, and we would like to make decisions on those points. So for example, trying to say which of these points belong to a car or person or tree when it comes to LiDAR for self-driving cars. So once again, this is similar to this application of computer vision in self-driving cars, but here instead we would use something like a LiDAR to get point clouds. And then working with graphs and machine learning on graphs. And I mentioned how we're seeing research in, when I talked about the problem with reasoning and machine learning, this is kind of how people are trying to use a machine learning agent, but being supported by some kind of facts. So for example, facts in the form of a graph, which expresses a relationship between things, like who painted a painting, for example. It can express as this kind of binary relationships. And then one of the interesting news, once again from DeepMind, this was late 2020, was AlphaFold. So being able to make much better prediction for the protein folding problem. So going from a sequence of amino acid and then predict how that will actually end up folded together in this complex way in three-dimensional space. Good progress has been done here. It is not a solved problem, but machine learning has shown that we can get far here in this problem, which from a traditional computational point of view is a very, very challenging problem. And then finally, some examples of what we call generative AI or generative models. This is also one of those new things in this cycle of AI, that we can train models to actually generate data or generate things which looks like the training data we have. So for example, you might have seen images of human faces that don't exist. So there was this website called This Face Does Not Exist, which generated images of very believable human faces with some artifacts. This has been done in a lot of different contexts. So for example, helping you guide some design process. And personally, I think this is where a lot of the interesting potential lies. This generative design that we see on the left-hand side here, similar principles can be used, for example, in the de novo molecular design. So trying to find molecules which have some desired property that these methods can now give you suggestions of new molecules. I see a lot of potential here. These methods do require huge amounts of data, but we can generate images, we can generate molecular structures, we can generate websites, we can generate music, we can generate text adventures, for example. So these are just some of the examples. And interestingly, so at least when it comes to these generative text methods, we've quite quickly seen kind of products being driven directly by the AI capability. Generating a text adventure is not a new thing, but people have previously typically used some kind of procedural algorithm. So using rules to try to generate content in computer games, for example, has a very long history. But we're now seeing it becoming really powerful. So for example, actually generating interesting text adventures. So that shows you some of the capabilities of AI. And while the first session here was kind of negative in a sense, that we said a lot of what you hear about AI is not true. It's a lot more limited than we are typically led to believe. I'm passionate about this. There is so much we can do. It's just that it's much more narrow. It isn't self-driving cars and it isn't Terminator, but we can still do things which were impossible 10 years ago. But then once again, back to kind of the negatives. So AI in practice. One of the things I started this session saying is that, well, we can think of AI in practice as a tool to automate something and build software to automate something. And so one of the points I will highlight here is that actually developing an AI solution for something is very similar to developing a software solution for something. Well, it is. We will develop some piece of software, and a lot of the kind of the experiences or the lessons learned from software development do apply to developing an AI tool. And here I'll start by highlighting some of the challenges with software development. So one of them is that one inherent thing one should be aware of is that software development often fails. So this is based on a annual report which a company called the Standish Group does. So it's a pretty well referenced report on essentially success of software projects. So they continuously go to software development firms and do surveys on what projects succeeded and what was the factors for why they succeeded. And one conclusion, this is from the 2015 report, but I do think these results still hold, that software development is fundamentally a risk. It is a challenge where complete success, having a project which is on budget, on time, and delivers satisfactory result only happens in less than a third of the cases. And projects which outright fail, you don't even get a software system at the end. You just put money in or wasted the money in a sense. It doesn't have to be waste. Typically these projects learn a lot about the business process you try to automate. But the risk of failure is high. So a fifth of project might outright fail. But there are differences in kind of what kind of projects fail and succeed. One important one I like to highlight, and it relates to AI, is that it is better to try to make a small software project. Large software development, it often fails. So we see that grand, really large project where you would like to, let's say, completely change your software system for a large organization, that is very, very risky. So here we see 43% of projects fail, while small projects, only 7% fail. And this, of course, has to do with complexity of the problem you're trying to implement software for. It really scales. It doesn't scale linearly with the size of the project. And to kind of tie this back together to AI, trying to, I started to show you this retrosynthesis, saying that we will replace this with software system is probably overshooting. Should probably try to focus is there some part of this which we could replace by a software system? And then how to actually develop software. Developing new software is always risky. So if you look at success depending on how the software was developed, developing from scratch using traditional languages and methods, or using modern methodologies, I would say that the difference isn't that large. They make a case for agile development here and perhaps for modern tools, but we can still say the success rate doesn't change much. But modernization, so updating a software actually has a much larger success rate. But that can be hard because perhaps you're looking to AI because there is no current software solution. It cannot be solved by traditional software, so there isn't anything to modernize. And then I think the important thing to keep in mind is that this will be a riskful project. There will be risks involved. And then finally, and I'll dig a bit deeper into this, key success factors for why projects actually succeed, so deliver on time, on budget, and give satisfactory result, is user involvement, executive management support, and clear statement of requirements. So when you state them like this, it's no surprise, but I would like to kind of focus on user involvement, where it's easy to perhaps, as one who would develop these things, so as an AI developer or AI software developer, it is easy, or rather, it is hard to understand what the user actually needs. So risk is that you end up with something like this, where the AI researcher, I have a pretty good idea of what I think would be really interesting things to see. And if the customer says, well, we need some kind of clothes for our workers, then perhaps what I come up with is something like the left-hand picture here. But what the user would really need is something on the right-hand side here. But perhaps there was a mismatch in communication about where the problem really was. I understood it was something with clothes and covering some part of the body, but I covered the wrong part of the body and in a way which didn't add utility to the user need. We have an example. So one of my colleagues who worked with anomaly detection, they visited a factory. So it was one of these manufacturing companies in Sweden. They visited the control room. There in the control room, on the control panel, they see this big lump of steel, here represented by this brick. And you have to excuse my shoddy Photoshopper here. But essentially, there's a brick lying on the control panel. And my colleague was kind of puzzled, well, what is this? And they call this, it's the, klumpen in Swedish, but chunk, perhaps. So it turns out they actually had an automated alarm system. So my colleague was there to talk about, developing an anomaly detection system, which is automated alarm system. But this automated alarm system never stopped alarming. So it gave an alarm all the time, which made it useless. But also it just made the operators, it was detrimental to their work. So they figured out a way to solve this, and that was to place a heavy object on the button which resets the alarm system, which then made it give no alarm. This is kind of an example of how problematic it is to develop something if you don't really have the user involvement. But now I don't know about the original alarm system, but likely they had some threshold which was set far too high, or sorry, far too low, so that it gave way too many false positive alarms. And if the system had been developed, in tight collaboration with the users, they would probably have pointed out that this is useless quite early. And then, so these are kind of some of the examples of why software is hard to develop, and kind of hopefully some examples of what contributes to software success. So AI is software systems, but there is an additional factor of success, and especially perhaps an additional factor of failure, which makes software system with AI a lot more risky, and that is, once again, data. So if there isn't any useful data for the project, it will fail. And for us, when we do applied machine learning with partners at RISE, the main hurdle is data. Because often what the partners might say is, we have a lot of data. So let's say it might be a government agency. We have a lot of the documents we would like to automate some information extraction on, or which we would like to categorize. But what they have is actually the waste pile. They have the rubbish pile. So in the document example, they might have PDFs. So if you want to do machine learning on documents you might have, if you have them in PDF, it is close to useless. It might be totally useless because those PDFs might actually contain images of text instead of actually containing text. But even if they contain text, they will be very hard to make use of. These steps of refining, going from the rubbish heap to this sorted waste, that will be very difficult. And also going from the sorted waste to actually extracting the gold, that will also be very costly. So this actually understanding your data is so important. And also I think this is likely important regardless of whether you want to do AI or not. You might have use of your data in understanding your process without involving AI, more of kind of a data science perspective. So then another report which instead tries to actually do more of the kind of research the Standish Group has done on software development. There haven't been much such research being done on AI and data science yet, but this is one I could find where they ask about 200 different data scientists working in different companies what their experience has been. This is kind of what were the challenges when it comes to AI or ML. So top one, it's what's more complicated than expected. And I should say that this was often people working inside the companies. These were often companies which were perhaps on the tech sector. So actually, they do have digital data, but still the problem was hard. And then lack of expertise, which is to be expected. But then problems with data is a very common one. And when they asked explicitly, was it challenging or was data a challenge, then 80% says that yes, data was a challenge. And then that biases and errors in the data was a big challenge. And I think this is unfortunate that when we teach machine learning and we teach data science to students, we often use very good data sets. They are ideal, they are super clean. While real world data sets often contain error. They might have missing fields. They might have perhaps a lot of the observation has actually entered the data incorrectly. So it's in the wrong column. So you have some values in a column, but those values should have been in another column. They will completely mess up the results because they have nothing to do with a column in the table that they say that they are. These kind of errors are quite common. Then not enough data not in a useful form, don't have the people needed to label the data, and don't have the tools needed to label the data. So these data, once again, I've kind of repeated myself, and I think we got a request that it would be interesting to see workshop more focused on these aspects, and I agree, talking about data. And another question which often comes up is kind of how much data you need. And I previously said that it's one of those unsatisfying answers that it depends. It depends on your process. So the behavior of the thing you want to model using these methods could be simple, well-behaved. You might not need much data, or it might be complex. There are lots of different behaviors that you would need to kind of cover. We can think of, we would like our data to be able to cover all of the variations in these lines. And we also talked a bit about this risk with adding more data. Well, the system I have is kind of like the pink one, and I only add all data I add is kind of from this region. I will have a system which perhaps misbehaves a lot. It will become biased towards that behavior, which will then, if my system starts to actually behave in different ways, will make this system, the AI I have implemented, completely wrong. These questions might actually need to run experiments. So perhaps you actually need to start doing an experiment with the data you have to decide whether your system is good or not. So to actually answer this question might actually need experiments. So finally, then some prerequisites for, being ready to work with AI. So as we said before, support from the people who make the decisions about whether to run projects or not, but also support from being desired by the users, that the users actually see a need for this tool. And then that we understand the process very well so that we can clearly specify what we would like the tool to solve. And then also resources to be made available. It's perhaps easy to think that we can hire AI experts from the outside, but often it's you will need your process experts to be involved. And then the question of data. You need to have high quality data or be able to generate high quality data. And then another question, do you need to develop your own system? And it also depends on how unique is the process or the problem we're trying to solve. Is it a problem a lot of people have? Let's say a problem which looks like someone else's problem. So classifying images, looking at an image and just trying to say whether is this image a cat or a dog. Sorry, it's a very common. Does this part produce include a defect or not? Is it defective or not? So those kind of systems, if you can just produce the data, so examples of defective parts or not, you can buy all of the kind of the software, all of the training and so on, and just you put in your data and you get a model which works quite well. So that is actually a relatively low cost development project. And also if you want to do things with, for example, categorized documents and your documents contain reasonably common language, that it looks like English, for example, looks like commonly used English on the internet, then these you can likely buy that solution. And then there are more specialized, there are companies who actually specializes in, for example, helping you with customer understanding customer satisfaction and so on. This I show you 3 examples here. This is from the 3 large tech companies in the sector, so Microsoft, Google, and Amazon. But I do think for a lot of the business process you might have, they might be quite unique. So imagine you have a plant producing parts. Perhaps there's no other place in the world which does the thing in the same way you do, because this has kind of grown organically over decades. So you might have to actually customize a solution. So the risks I've talked about here do apply. And I think for a lot of automating processes with AI, that might be the case. So that's kind of, I will now kind of leave the pessimistic tone and talk more about perhaps what can we do in practice. So now I've talked for a very long time, but Jeanette, I will.
Yes, now we're going to talk about 3 examples that we have met both in different ways when we are meeting companies. If we start with a small company, and maybe typically we choose tourism. And we start always, you said, what need to be done, the hygiene factors firstly, and then we start focusing on the problem. At what is the problem? Is it to have the right customers, to increase sales? What is the real problem? Because it's easy to start with what data do you have, but when we meet them and we talk about them, what the need, when we have kind of single out, this is the problem, what can we do to help them then? And when you meet someone like comes to you, Eric, and said, okay, now I've been to this seminar and I can see that I can use maybe some kind of search engine, or can I have someone kind of recommend my launch to everyone that goes to look at the Tree Hotel site, and then they will be direct to me. Is it possible? What data do I need? Can I do this? How shall I do it?
Exactly, and I think a lot of small companies might feel that way. So, okay, everyone is talking about AI, so I should probably also do AI. And I do have a lot of problems where I do think AI could be useful. But here I think it's kind of the question of, should all companies do software development? And they probably shouldn't. Mainly because they aren't large enough. They might really benefit from having, if they were able to have in-house, developers, that might really be beneficial, but it's not realistic. So I do think for a small company, when it comes to AI, I think right now and probably in the future, it will be kind of like it is for any software service now. If they are not in the software business, they will likely buy these things. So for example, they might say that, okay, we need to reach the right customers. Well, the right way is probably to go through one of the perhaps marketing companies. Going directly to the big ones you can do, but you could also collaborate with the small ones which do other kind of marketing, but they can also do marketing driven by AI. So and then what kind of data do you need? Do you need your own internal data? Perhaps you do, but often not as kind of input to training the algorithms, but perhaps input for a human to try to understand what is actually our customer, what kind of customers do we have, so that I can try to then, when I talk to my the marketing company I have hired, I can tell them what kind of people we would like to reach out to. So it's more like it's still about understanding my data. And I said previously that I think think about data is probably important, not only if you want to do AI, but I think this is an example where understanding your data helps you buy the right service, the service which will not use your data directly, but is you will get better utility from that. So and I guess this also kind of answers the last question, that you might not actually have to care that much about the AI being used. What you should care about is probably more, can you measure the performance of this? If it is marketing, can you measure that performance, and how can you measure that? Because perhaps there is the risk that if it is online marketing, that it isn't actually useful. So I think then it helps to actually have not going directly perhaps to Google, but actually going to someone which can, for you, make sure that the marketing being paid for is actually useful and efficient. Actually drives new sales, because that has been observed as being an issue, that some companies cut down on marketing by 90% during the pandemic and didn't see sales being affected, online marketing. So the question is, was the online marketing successful? And it's hard. Marketing has always been hard.
Yeah, thanks. And if we continue to bigger companies that maybe have more people working in them and are in that way have maybe departments even that collecting data, and it's also starting here with identifying the problem. What is the problem that hurts the most and it can be different things. I mean, like you said, in the pandemic, a lot of companies couldn't keep up with the demand of different kinds of things, and also some things that we talk about is maybe just work environment and what is the problem, and when they have data and when they have started this, what and they have some kind of idea, what's the next step then?
Yeah, so first identifying problem, and as you say, that is key, and it's also something that needs to be done by the company or by the organization. So what is needed? Well, if it's, let's say it can't keep up with demand, then likely you need to focus and find out what could you do to improve, increase production. So do you have some bottleneck in productivity which you could try to eliminate using these automation tools? And would it be, would the efficiency gain be worth it? And then the question is what that is. Well, perhaps it can't keep up demand, perhaps it is actually tied to returns. So it's a quality issue. Too many of you produce a lot of things, and if the quality was higher, you would be able to satisfy demand. And also the returns are an extra cost. So perhaps it's actually about quality assurance or quality assessment. And could you automate quality assessment? Perhaps there could be a lot to gain. So first, you would reduce the number of returns, but perhaps that would be one step to then trying to understand what leads to these imperfections. Because once you have an automated quality assessment tool, you can start to have kind of an online quality measurement, which is very hard, which you can then start to by using data analysis, correlate to try to find a cause in your process. So I mean, this is a large project. This is not something you do very quickly. If demand changes very quickly, but at least that's one way of attacking it. But it really has to do what's the source for what's the reason for why you can't keep up with demand. And the workplace environment. There, I think there is things one could do. It really depends on the workplace, what it is, and there is this risk of that if the workplace environment, if the issues are perhaps on a social level, I think AI will have a hard time doing anything about that. But if it's more about perhaps hazards and risks, then actually monitoring the environment and being able to flag for dangerous situations might be useful. So if you do have video data of your environment, you might be able to use this kind of, as I showed you, this video monitoring tools to try to see whether you have, environments which are risky or where you could actually perhaps intervene before a real injury happens.
And this is also something that if you include the people, that work is going to be changed with using more automating, either in robotics or in software. Then you get right. Not just talking about efficiency, because when people hear efficiency, it feels like, okay, I'm going to lose my job to a machine.
Yeah. No, that is very true. So for example, I talked about quality inspection. A lot of it is done manually. So by doing samples, random samples, and then a human might sit with a microscope and examine images for hours on a day. Horrible work conditions. So if that could be automated, that would be actually a real gain in workplace environment. Or also, that is kind of tedious in a sense, but there might also be hazardous steps in a process which you could automate, not necessarily because of efficiency, but because of safety.
Yes, and I think we'll go to the next, since the time to bigger companies. I mean, a lot of this is really something that is important, that we have always kind of automated things that are simple, and that's something maybe to start with when you're thinking of what can we automate, what is repeatingly and what is simple. That is the best thing to start with. And when it comes to, we work a lot with the government agencies, and it's the same. I mean, sometimes it's more people that work in the government agencies. They sometimes see that industry has it's easier, and they include people more in decisions. If, for example, when you automate with a machine. And in government agencies, we have so many. We have 290 different municipalities. We have 300 different authorities. So we have so many different problems. So here is the real, also super important to have this identify the problem and also see how can we have this, because we need to have transparency and no bias and all of this. And some people really think that having computers is going to reduce bias and also reducing the people that call handläggare. I don't remember what this in English.
No, I don't know the English word either. So if someone knows, please help us out.
Yeah.
But the person doing the processing essentially of the, or making the decisions. Yes, I agree. And as you said, and I think it's important to highlight once more, the stupidest and simplest thing, and perhaps the most tedious thing. So once again, I think it's important to drive this change. It needs to also be driven from below, so that you probably from the users or the people actually doing the work, you might get a good idea. They are the ones who might have an idea of what they would like to see automated. Now perhaps that might not be strategically the best thing to do, but it's a good place to start. And it should be a routine. It should be simple in a sense. It should not require contextual knowledge about humans or understanding of culture or understanding of how do doctors formulate themselves and these kind of things. So I think there is of course a great desire to introduce automation in these contexts, but I think it is a huge challenge, and I also think we should ask ourselves really whether we should. This is really when we get back to kind of the ethics. It will likely be it will be a misconception that these things will be better than humans. While they might be cheaper, the decisions they make might be very wrong, might be much worse.
Yeah. And to this area, the Swedish government also puts money and others, because this is really something that concerns all of us. So it's a really important area. And I think we'll wrap up with where to start.
Yeah, so I have 2 more slides, kind of, they do repeat what I've said before, but where to start. And as I mentioned many times, data is really the break or make factor. Without it, it doesn't matter whether, what else you do, essentially. If you don't have data, you will not succeed. But I think one thing, and the reason this e-waste analogy, which I made up or came up with, why I like it, is because I think similar attitudes as we have towards waste management, we can have towards our data management. So we can think about, regardless whether we have AI projects starting or not, we can think about the data we produce as similar to the waste we produce. So eventually, someone might want to do recycling, so to say. Someone might want to use this waste for something. So perhaps if we think about whether we can actually structure our data gathering so that we kind of have multi-stream recycling instead of single-stream recycling, then the effort we need to put into this sorting of the data later will be much lower. So perhaps there is actually, we will not have to pay as high a cost. And I mentioned this problem with PDF documents. This has really shown once again and again that if the electronic data have been saved in tables originally instead of being put in a document and then converted to images, the cost would be much lower. Yes, perhaps we can use OCR, optical character recognition, to try to get back the text which is in the image. We can do that, but the cost will be so large so much larger that it can't motivate actually doing this thing we would like to do with this data. So really trying to early on do a good kind of recycling process, I think, is important. And then another, where do you start with automating the processes? And I said again and again, I really think involving the users is really key. And I'm hugely in favor of trying to educate your experts, the experts on your process, try to educate them in AI instead of trying to educate the experts in AI in your process, because I think the latter is much more complicated. Real world processes tend to be very complex, at least the ones I come across with. And as kind of an AI expert, I'm again and again kind of struck by how complex each and every organization is, and often in different ways. So each organization have different complexes in their processes, which makes it very hard to, as an AI expert, perhaps having looked at one organization and their decision-making process of, classifying patterns, and then looking at some completely different organization, what I learned at the first one will not transfer to the second one. And also to come up with what are actually good process to automate. I think the users are the ones who can drive that. But in the end, you ultimately need experts in AI as well. So you will need some kind of interdisciplinary team. But I think it's a good idea to start with the people you already have who understand your process. And then finally, why I arranged this seminar, and I mentioned at the beginning that there has been a lot of hype around AI. And while we've seen a lot of, sorry for this kind of wall of text, but I'll walk through it. I think mostly it's been about how we communicate about AI, and perhaps also that it does kind of jog our imagination. It is fascinating to think what we could do, and we easily start to kind of extrapolating, becoming science fiction very easily when we talk about AI. So, for example, we said we saw a real advancement in computer vision from 2010 to about 2014 and 15. We saw that as kind of computer vision is solved. Computers will now be able to learn through the world by seeing it. But it turns out that computer vision wasn't really solved. And it was much harder to learn from the world by just seeing it. So there was a meme just last week of Elon Musk, the founder of Tesla, talking about self-driving cars and promising it for the next year, for the almost last 10 years. And I don't think sure, it's part marketing, but I do really think Elon Musk is convinced that it's just a year away, because it's so easy to be kind of wrapped up in the excitement and the possibilities of what we're seeing happening today and extrapolating that. But then also marketing, I think there is a lot of bad marketing about AI, which tries to drive on the hype, to try to tell people that what you're seeing actually does more than you think. And I use Watson here as an example because I think it's quite telling. So Watson won Jeopardy in, I think, 2011. And this got a lot of attention because a computer beat a human in general world knowledge. What people thought. But in reality, Watson was just a well-made search engine, which which pretended to be human by taking in human text and generating something which looks like human language. But underneath the hood, it's very much just a well-engineered search engine. Using AI techniques, using machine learning definitely, but not being able to do the things which it was marketed as being able to do, to solve cancer or to Watson Health really oversold that a lot, and really oversold what people could do with Watson, and giving the impression that Watson was one AI, while in reality Watson was more of a department of skilled data scientists, which would try to tailor the data science software to your problem, and often encountering the exact same problems as you do in the data quality problems. That even though, I mean, you don't generalize from answering Watson to being able to replace a doctor. But then also we talked about these societal changes, and I think this is really important, that we want more people to think about these things and be engaged in them. And we want also, when we work with organizations, we want the kind of the foundations to be better, especially when it comes to data.